Good evening, students. Welcome back to the chemistry class. In the previous class, we have discussed the classification of elements based on atomic weight as well as based on atomic number. The current classification of elements, it is based on atomic numbers because the properties of elements, they are dependent on atomic number rather than atomic weight. So in today's class, we will discuss what is meant by periodicity, what are periodic properties, and how they change along a period down the group, and what is the reason for the changes. So let us see what is meant by periodicity. Generally speaking, anything that gets repeated at regular intervals is called as a periodicity. Say for example, in a year, seasons. How many seasons are there? Summer, rainy, and winter. If we take the main seasons, every year these seasons are repeated at regular intervals of time. Say for example, summer in India generally begins in the month of March and continues up to June. Rainy season is supposed to begin from July and extend up to November, and winter December to February. So within 1 or 2 weeks of variation, in general, every year the seasons repeat during these time intervals. This itself can be taken as an example for periodicity. Similarly, you take your classroom. Timetable is the best example for periodicity. Every day at fixed intervals of time, the subject sessions keep on changing, and they are also repetitive in nature at regular intervals of time. So timetable also can be taken as an example for periodicity. Now, what is meant by periodicity with reference to periodic table or with reference to elements? In the periodic table also, particularly in modern periodic table, properties of elements get repeated at regular intervals. These are the regular intervals: 2, 8, 8, 18, 18, 32. These numbers are also referred to as magic numbers. What is meant by magic numbers? At these intervals, the physical as well as chemical properties of elements get repeated. So just for example purpose, I will give you one case. You take the elements of first A group. The elements present are hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So, inorganic chemistry generally appears to be a memory-based subject, but you need not memorize many things. Just in a sequence order, they keep on flowing as it is. Say, for example, you want to know the atomic numbers of these elements. Just you remember the atomic number of first element of any group. To that, keep on adding these magic numbers in a sequential order. It will give you atomic numbers of rest of the elements in the periodic table. Say, in first A group, hydrogen atomic number is 1. 1 plus 2. It will be the atomic number of lithium. Next, 3 plus 8 will be the atomic number of sodium. 11 plus 8, atomic number of potassium. 19 plus 18, the atomic number of rubidium. 37 plus 18, 55. The atomic number of cesium. 55 plus 32, 87. So, like this, atomic numbers of consecutive elements of a group can be calculated by using these numbers. One more aspect is at these intervals of atomic numbers, what happened? Elements belonging to the same group appeared and they are together. And the elements present in a particular group, they will have similarity in chemical properties, regular change in the physical properties. So this kind of repetition of properties at these regular intervals of atomic numbers is called as periodicity. And whatever properties that get repeated at these intervals of atomic numbers, they are referred to as periodic properties. The properties of elements which get repeated at these regular intervals of atomic numbers are referred to as periodic properties. So total how many periodic properties are there? That we have to study in detail. Some of these properties maybe you came across at a school level itself. So here we will study them in detail. Atomic radius. In turn, this atomic radius is responsible for atomic size. Generally, size means we take it as equal to volume. Volume is based on radius of the element. Right? Then, second property is ionization energy. Ionization energy is sometimes also referred to as ionization enthalpy as well as ionization potential. Then, third property is electron affinity. This electron affinity is also referred to as electron gain enthalpy. So this term enthalpy later you will come to know in detail in the topic thermodynamics. For the time being, just remember that energy and enthalpy, they are synonyms, similar terms. Then electronegativity, electropositivity, metallic and non-metallic nature, acidic and basic nature of oxides, valency. Valency can also be taken for equal to oxidation state. They are not exactly same, but they are closely related with each other. Then, one more periodic property is diagonal relationship. So, these 9 properties are commonly called as periodic properties. Atomic radius, ionization energy, electron affinity, electronegativity, electropositivity, metallic and non-metallic nature, acidic and basic nature of oxides, valency, also known as oxidation state, and diagonal relationship. So we have to see what is the meaning of these properties, how they change along a period, how they change down the group in detail. So let us see one by one. First, let us begin with the atomic radius. Atomic radius. It is defined as distance from the center of nucleus to the outermost orbit. Distance from the center of nucleus to the outermost orbit is called as atomic radius. So, what do you mean by outermost orbit? Wherever the last electron is present, that is referred to as the outermost orbit. Say for example, you take hydrogen atom. Hydrogen atom atomic number is 1, means it is made up of one proton and one electron. So hydrogen atom you can visualize like this. This is the nucleus. This plus symbol is indicating proton, and this represents first orbit in which one electron is rotating. So now this first orbit itself will become outermost orbit for hydrogen. Now we have to take this distance, what we call distance from the center of nucleus to the outermost orbit. This distance will be taken as equal to atomic radius. Now suppose you want to calculate atomic volume, which is also referred to as atomic size. These atoms, they are supposed to be spherical in nature. So volume of sphere is calculated by using the relation 4/3 pi r cube. So in this, in place of r, if you substitute this distance, it will become atomic volume. Now say you take the another element. Say for example, you take lithium. Lithium atomic number is 3. That means 3 protons and 3 electrons are present in this atom. Now lithium atom, how we can visualize this? 3 protons are present inside the nucleus, 2 electrons are present in the first orbit, and 1 electron is present in the second orbit. So for lithium, outermost orbit means second orbit will become the outermost orbit. Now, if you measure the distance from the center of nucleus to the outermost orbit, it will become atomic radius of lithium. Say you take the next element, sodium. Atomic number is 11. So how can you visualize? 11 protons are present inside the nucleus, 2 electrons in the first orbit, 8 electrons in the second orbit, 1 electron in the third orbit. So for sodium, outermost orbit means it will be third orbit. Now take this distance, that is called distance from the center of nucleus to the outermost orbit. That will become atomic radius for the element sodium. So like this, it is a theoretical aspect. Practically, is it possible to measure this distance or not? that is secondary, but we can visualize atomic radius like this as distance from the center of nucleus to the outermost orbit. Now, what are the difficulties in measuring this distance as per the definition that we will see separately. Now, coming to periodicity regarding this property. Periodicity means how this particular property is going to change along a period and down the group. Along a period, atomic radius decreases. Down the group, atomic radius increases. That is the periodicity. Now, the question is why atomic radius decreases along a period and increases down the group. Let us take an example. Say you take elements present in second period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So here atomic numbers of these elements are increasing in a successive manner. So lithium atom, how we can visualize is like this. 2 electrons and 1 electron. So for lithium, atomic radius means distance from the center of nucleus to the second orbit. For beryllium, it is 4 protons inside the nucleus, 2 electrons in the first orbit and 2 electrons in the second orbit. So here also atomic radius means distance from the center of nucleus to the second orbit. Boron, 5 protons, 5 electrons. Out of 5 electrons, 2 are present in the first orbit, 3 are present in the second orbit. So here also distance from the center of nucleus to the outermost orbit, that is to the second orbit, can be called as a distance from the center of nucleus. Now you may get a doubt. We have given the statement that atomic radius decreases along a period. But as per these diagrams, it should remain constant because it is distance from the center of nucleus to the second orbit in all these cases. But what you should observe carefully is, no doubt, number of the orbit is not changing, but number of protons present inside the nucleus is changing. In fact, it is increasing in a consecutive manner. As a result of this increase in the number of protons inside the nucleus, effective nuclear force of attraction increases. As a result, the outermost orbit is somewhat pulled towards the nucleus. That is why, as we move from lithium to fluorine, continuously there will be decrease in the atomic radius. From fluorine to neon, there will be sudden increase in the values. This sudden increase from fluorine to neon is due to the completely filled orbitals. In case of neon, 8 electrons are present in the outermost orbit. Because of this completely filled nature, there will be inter-electronic repulsive forces operating between them. As a result, from fluorine to neon, there will be sudden increase in the size. So, generally speaking, what we can say, atomic radius decreases along a period. In a given period, largest atom always belongs to first A group, and smallest atom always belongs to seventh A group. So this is applicable in any period. Now coming to variation down the group. Down the group, atomic radius increases. Why it increases? Let us take an example and see. Suppose you take the elements of first A group. Elements present are hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Atomic numbers are 1, 3, 11, 19, 37, 55 and 87. So hydrogen atom we can imagine like this. So for hydrogen, atomic radius means it is distance from the center of nucleus to the first orbit. When it comes to lithium, 3 protons are present inside the nucleus. 3 electrons are distributed like this. 2 electrons in the first orbit, 1 electron in the second orbit. So for lithium, atomic radius means distance from the center of nucleus to the second orbit. Similarly, sodium, if you take 11 protons inside the nucleus, 2 electrons in the first orbit, 8 electrons in the second orbit, and 1 electron in the third orbit. So, for sodium, it is distance from the center of nucleus to the third orbit. Like that, in a successive manner, what happens as we move down the group, one new shell will be added. And because of this, one more thing what happens is, even though number of protons inside the nucleus are increasing, because of these inner orbits and inner electrons present between nucleus and outermost orbit, effective nuclear force of attraction actually decreases. So, as a result, atomic radius continuously increases down the group. So, in most of the cases, this variation is common. As we move from top to bottom, atomic radius always increases. Let us see the practical values to get the concept clearly. Let us see the actual values observed for elements. Let us take one particular period. Second period, if you take, the elements present in it are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. If you look at their atomic radius values, lithium has 0.53 angstrom units of lithium has 152 picometers of atomic radius. Beryllium has 112. Boron has 85. Carbon has 77.2. Nitrogen has 70. Oxygen has 73. Fluorine has 72. Neon value is 71. So these are all picometer values, and this is atomic radius. Even though it's atomic radius, it is generally considered as equal to covalent radius. That we will discuss separately. So more or less, as we move from lithium to fluorine, the size or radius has gradually decreased. Now, let us take a particular group for comparison. If we take the elements of first J group, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Hydrogen atomic radius is 37.1 picometers. Lithium 152 picometers. Sodium 180 6, potassium 227, rubidium 248, cesium 265, francium. For radioactive elements, generally physical constant values will not be available. So, to exclude francium as it is radioactive in nature. So here, if you see the atomic radius values, how they are changing, they are continuously increasing. The reason for this continuous increase in atomic radius is addition of a new shell in a successive manner and at the same time decrease in the effective nuclear force of attraction as we move down the group. So this is how the first property, atomic radius, changes along a period as well as along a group. So what we can say as generalization is, in a given period, the largest element always belongs to first A group and smallest element belongs to seventh A group or halogen family. Next, ionization energy, also called as ionization enthalpy, as well as ionization potential. In short, you can call it as IE as well as IP. So it is defined as the amount of energy required to remove an electron from neutral gaseous atom. The amount of energy required to remove an electron from neutral gaseous atom. It is referred to as first ionization energy. Theoretically, any element can have n number of ionization energy values, where n represents total number of electrons present in that atom. So, various ionization energy values can be represented as IE1, IE2, IE3, IE4, like that up to IEN. So, this definition is applicable for IE1. So, let us try to understand what is meant by this statement. Say, for example, if you take hydrogen atom, its atomic number is 1. How can you visualize hydrogen atom? One proton is present inside the nucleus and one electron is moving around it. Now, there is attraction force between the nucleus and the moving electron. Because in the absence of nuclear force of attraction, simply the electron will fly away in the tangential direction. But it is not happening continuously, it is moving in a fixed orbit at a fixed distance. That means there is an attraction force operating between the nucleus and the moving electron. Now, to take out this electron from the nuclear force of attraction, we have to spend some energy. How much of energy you are spending to break the nuclear force of attraction and make the electron a free bird? That is what is meant by ionization energy. And in case of hydrogen, as there is only one electron, how many ionization energy values are possible means only one is possible, and that is represented as IE1 or first ionization energy. Now, By removing this electron, hydrogen atom will become H plus ion. This H plus ion is known as hydronium ion. And hydrogen by nature is present in gaseous state. While defining ionization energy, compulsorily the element must be in gaseous state. If it is not in gaseous state, first it should be converted into gaseous state, and then we have to measure the energy required for the removal of electron. Now, let us take one more case. Let us take a lithium atom. Atomic number of lithium is 3. So, this lithium atom can be imagined like this. 3 protons are present inside the nucleus. 2 electrons are moving in the first orbit, and 1 electron is moving in the second orbit. And as it is, atom is neutral. Lithium physical state is solid. To measure its ionization energy, first it needs to be converted into gaseous state. Now, if we imagine that lithium is in gaseous state, how much of energy you have to spend to take out that electron? That will be called as IE1, first ionization energy. Then lithium atom gets converted into lithium ion. And for this conversion, whatever energy was spent, that is called as IE1. Now, from uni-positive lithium ion, if you take out one more electron, it will become di-positive lithium ion. And this will be in gaseous state. For this conversion, energy required will be equal to IE2, second ionization energy. Then, theoretically, from di-positive lithium ion, one more electron can be removed. Then it will become tri-positive lithium ion. And energy required for the purpose will be called as IE3. So, as the magnitude of positive charge is increasing, successive removal of next electron becomes difficult. That is why successive ionization energy values continuously increase. So, say in case of lithium, IE3 is greater than IE2 greater than IE1. So here, how the questions come is, they will give successive ionization energy values. We have to identify what is the valency of that particular element. So, while removing the electrons in a successive manner, if we come across a stable electronic configuration, that ion will be stabilized. As a result, the removal of next electron becomes difficult. Therefore, there will be sudden increase in the ionization energy value. Say for example, lithium you take. Let us assume that IE1 is some 100 kilocalories per mole. IE2 value will be some 300 kilocalories per mole. And IE3 value will be say 400 kilocalories per mole. Now, if you see 100 to 300 means it is abnormal increase, but 300 to 400 means not abnormal increase. So, wherever there is abnormal increase, that indicates stabilization of the ion formed by means of electronic configuration. So, here if you see with the loss of one electron in the outermost orbit, the lithium ion formed gets a stable electronic configuration 1s2, which is a configuration of helium. This configuration is also called as a doublet, which is highly stable. So, to disturb that stability and to take out one more electron, you have to spend extra energy. So, like this, wherever abnormal IP values are observed, for an element, that abnormal increase state can be taken as equal to its valence. So finally, concluding remark is any element can have n number of ionization energy values, and in a successive manner, these ionization energy values will increase because of increased nuclear force of attraction in a successive manner. And how these ionization energy values change along a period and down the group. Ionization energy is dependent on atomic radius in this manner. Ionization energy is inversely proportional to atomic radius. Just now we have discussed, as we move along a period, atomic radius is decreasing. So when atomic radius decreases, ionization energy value increases. Down the group, atomic radius is increasing. Therefore, ionization energy value will decrease. In a given period, always corresponding zero group element will have highest ionization energy. In a given period, lowest ionization energy will be associated with first group. That is 1A group or alkali metal family. And down the group, ionization energy continuously decreases, and along a period, ionization energy continuously increases. So that is the general trend of variation of ionization energy values. So what we have discussed is, we have defined ionization energy. We have seen how many types of ionization energy values are possible and how their values keep on changing, and how period this ionization energy changes along a period and changes down the group, and how to predict valency of an element by means of ionization energy values. Next periodic property is electron affinity. Electron affinity is also known as electron gain enthalpy. This can be considered as a reverse property to ionization energy or opposite property to ionization energy. The term is defined as the amount of energy released when one electron is added to the outermost orbit of neutral gaseous atom. For taking out electron from neutral gaseous atom, we have to spend energy. This is reverse process. When you add one electron to the outermost orbit of a neutral gaseous atom, what happens? Energy will be released. Why energy is released is because when an extra electron is added, the potential energy of the system decreases. So the difference in the potential energies of a individual atom and the corresponding anion produced will be equal to electron affinity. So theoretically, any element can have n number of electron affinity values. But instead, like ionization energy values, the successive electron affinity values keep on decreasing. Why? Because in case of first electron affinity, we are adding an electron to neutral gaseous atom. Say some element A is there in gaseous state. We have added one electron. Because of that, A has become A minus, uni negative anion. And in this process, whatever energy is released will be called as electron affinity, or we can say first electron affinity. Now, assume that to the resultant uni negatively charged ion in gaseous state, we are trying to add one more electron. Then it should become A minus 2 di-negative anion. But in this conversion process, energy will not be released, but energy will be absorbed. So here, if energy change is negative, here energy change will become positive, indicating this process is endothermic in nature. Reason is, in the first case, we are adding a negatively charged particle electron to neutral gaseous atom. So here repulsive forces will be at its minimum level. But in the second process, already that ion has acquired negative charge and you are trying to add one more negatively charged particle. Therefore, there will be repulsive forces between the incoming electron and the anion. To overcome those repulsive forces, we have to spend additional energy. Then, by force, this electron will be added to that ion, and you may get the by negative anion. So that is why successive electron affinity values keep on decreasing. So, electron affinity and ionization energy, as they are opposite processes, particularly first ionization energy and first electron affinity values can be correlated. They are quite opposite in nature. So just you change the sign convention, ionization energy becomes electron affinity becomes ionization energy. So how this electron affinity changes along a period and down the group. Most of the periodic properties, they are dependent on atomic radius in one way or the other. Electron affinity is inversely proportional to atomic radius. That means if atomic radius increases, electron affinity value decreases. This relation is similar to the relation between ionization energy and atomic radius. So, as you move along a period, atomic radius decreases. Therefore, electron affinity value will increase. As we move down the group, atomic radius increases. Therefore, electron affinity value decreases. Generally speaking, in a given period, element with the least electron affinity value belongs to first A group and element with the highest electron affinity belongs to seventh A group. But this atomic radius relation is not exactly correct in all cases. We say optimum atomic radius must be there so that electron affinity value can have sufficient value. Say for example, if you take 7th A group elements, fluorine, chlorine, bromine, iodine, astatine. Astatine being radioactive will keep out of discussion. So here atomic radius continuously increases down the group. So what we should expect is fluorine should have highest electron affinity followed by rest of the elements. But practically observed phenomenon is chlorine has a highest electron affinity. Then it is followed by fluorine and the rest of the elements. So as per this relation, this must be the correct statement. But practically observed values indicate that element with highest electron affinity is chlorine but not fluorine. Reason is optimum atomic radius. In case of fluorine, atomic size is too small. As a result, there is not sufficient space to accommodate the incoming extra electron. So there will be inter-electronic repulsions between the incoming electron and valency electrons present in fluorine already. But in case of chlorine, size has slightly increased. So in case of chlorine, sufficient space is available for the incoming electron to accommodate. As a result, chlorine can readily accommodate incoming electron compared to fluorine. But when it comes to bromine, along with size, we have to consider what nuclear force of attraction also. If you apply the same logic applied for fluorine and chlorine, we must say that bromine has a higher electron affinity than chlorine. But fact is its electron affinity is less than